Hi everyone, this is lesson 1-1, video 1.1.5. Our learning target for this video will be for students to be able to state the domain of a function. In example 5, we are going to find domains algebraically. In example A, we are going to state the domain of the function g of x equals square root of 4x minus 1. Now, to find the domain algebraically for this function, we need to figure out what values of x are allowed to be plugged in for this function g of x. Now, remember, the domain of a function are the x values that you're allowed to input into the function so that you do get an output. Now, one thing we need to do is think about what values can go underneath a square root. A square root can only be 0 or a positive number. So we know that 4x minus 1, the expression that we have underneath the square root, right here, can only be 0 or larger than 0. So what we want to state is that 4x minus 1 has to be greater than or equal to 0. And now what we want to do is figure out what x values satisfy this inequality. To do that, we are going to solve this inequality for x, or get x by itself. So I'm going to go ahead and solve for x here by adding 1 to both sides. Solving an inequality is the same as solving an equation, with a few minor differences in that if you multiply or divide by a negative number, you have to change the direction of your inequality. We won't have to do that in this example. We won't be multiplying or dividing by a negative. So I'm going to add 1 to both sides. That tells me 4x is greater than or equal to 1. And then since I'm multiplying x by 4, I'm going to divide both sides by 4. And over here, x is greater than or equal to 1/4. Now, what this is telling me is that our domain, we are only allowed to plug in x values in this function that are greater than or equal to 1/4. Now, going back to when we talked about interval notation last week, I talked about how the reason for learning set builder and interval notation were to describe the domain of your function. So I really have two choices here to describe the domain of my function, or to state the domain of my function, and that is to say the set of x such that x is greater than or equal to 1/4, comma, x is an element of the real number system. Now, if you think about the graph for this function, we have 0, and maybe we have 1/4 right here and 1/2 right here. And since 1/4 is included in this inequality, we can go ahead and circle, put into closed circle on 1/4, and then shade all the numbers greater than 1/4. Because after all, we're saying that the solution to this problem is that x is greater than or equal to 1/4, so I'm going to shade all the numbers greater than 1/4 on the number line. Now, if I was going to write the domain, we already wrote the domain in set builder notation. If I was going to write the domain in interval notation, really the interval for x is greater than or equal to 1/4 is bracket 1/4, comma, infinity, parenthesis, because we are shading from 1/4 all the way to the right infinitely, so we'll shade to infinity. Which infinity isn't really a number, so therefore we use a parenthesis around infinity. In example find, we want to find domains algebraically, and we are going to state the domain of the function. Okay, this time we have the function h of t equals 3t squared divided by t squared minus 1. Now, in this example, we have a fraction rather than a radical or a square root. And one thing you always have to worry about fractions is dividing by 0. we never want the denominator to equal 0. Okay, so if we never want the denominator, which is the bottom of a fraction, right here I'm going to go ahead and we're talking about the denominator in this function as being t squared minus 1. So if I take t squared minus 1 and I never want it to equal 0, I'm going to say can't equal 0. Okay, I don't want t squared minus 1 to equal 0. So I'm going to go ahead and figure out what values of t are going to make this function 0. The reason why I'm solving for t in this example instead of x is that t is our independent variable. Instead of using the function h of x, using x as their independent variable, this time they're using t as the independent variable, so therefore I need to figure out, in order to figure out the domain, I need to figure out what values of t I can plug into the function so that I get an output or a value for h of t. Okay, so in this example, I'm going to try and figure out what values of t make t squared minus 1 equal to 0, or in other words, I don't want t squared minus 1 to equal 0. So I'm going to go ahead and solve this equation by adding 1 to both sides, and I get t squared cannot equal 1. And if I square root both sides, we know that from solving an equation, if I take the square root of both sides of an equation, I need to put a plus or minus in front of our solution. So therefore, I don't want t cannot equal plus or minus square root of 1, which implies that t cannot equal plus or minus 1 because square root of 1 is 1. So what I'm saying in this example is that t cannot equal 1 or negative 1. Now, if I look at that, here's the reason why. If I evaluate the function, I'm going to go up top here at the top of the screen. H of 1 is equal to 3 times 1 squared divided by 1 squared minus 1. If you evaluate that on top, we end up with 1 squared is 1, 1 times 3 is 3, and on bottom, 1 squared minus 1 is equal to 0. Well, what happens is dividing by 0, if I try to take 3 divided by 0, that cannot occur. You can't take 3 and divide it by 0. You can't take something, or 3 of something, and divide it into 0 groups. So therefore, h of 1 does not exist, right? H of 1 does not exist. I'm going to use DNE for does not exist. H of 1 does not exist, and neither does h of negative 1, because even if I plug in negative 1 down here rather than positive 1, I would still get negative 1 squared minus 1, which is 1 minus 1, which is still going to give me a 0 in the denominator. Now, to state our domain, we have a couple options here. To state our domain, we are going to state in set builder notation the set of t such that t does not equal plus or minus 1 and t is an element of the real number system. T can equal any other value in the real number system except for these two values I've stated right here, which is positive and negative 1. On the next slide, I'll go ahead and write out our domain in not set builder notation, interval notation. So we decided in the previous slide that t could not equal positive or negative 1, and therefore our set builder notation was t such that t could not equal plus or minus 1, and t was an element of the real number system. Now, for interval notation, if I think about what this means, I can shade any number on this number line that I want. Let's call this number line t, because that's the variable they used. And I want to only exclude -1 and +1. So I'm going to put an open hole on -1. I'm going to put an open hole on +1. And then I can shade the entire line because every other number is able to be used in our domain. Okay, every other number is an element of our domain. So here's the thing. I really have 3 regions that I'm shading here. And we're going to start from least to greatest. So over here is -infinity. Over here is +infinity. I'm going to shade from -infinity until I reach -1. So I'm going to say my domain is -infinity to -1. Union. Because now I shade again. After -1, I shade from -1 to +1. And union from 1 to infinity. Now notice I use parentheses all the way through. That is because -infinity and +infinity cannot be included because infinity is not a number. It's just a symbol used to describe something that's increasing or decreasing without anything restricting it or stopping it. And -1 and +1 are not included on the number line. Therefore, I would use parentheses around those stopping points. Okay, so I'm going to shade from -infinity to -1, not include -1, shade from -1 to 1, not include either of those values, and again, shade from 1 to infinity and not include 1. So this is my domain right here. And this domain really describes all of the x values, not x values, the values of t, rather. Normally they use x as the independent variable, but this time they chose to use t as your independent variable. So therefore, we're going to say the domain is describing t. So again, here's the domain and set builder notation. Right here we had set builder notation, and at the bottom here we had interval notation. And I don't care what notation you use, really you should be able to write the domain in both interval and set builder notation. In example 5, we're asked to find the domain algebraically of the function f of x equals x minus 5 divided by the square root of 2x minus 3. Now this time, in this example, you kind of have a double whammy. You have a radical in which you have to worry about there being a negative underneath the radical, as well as you have a fraction, in which case we know that the denominator cannot equal 0. Okay, so this whole thing right here, I'm going to circle right here. This whole thing on the bottom, it can't be negative because the radical. We don't want a negative underneath the radical because we can't square root a negative number. And we don't want it to equal 0 because we can't divide by 0. So what we need to do is we need to state that 2x minus 3 has to be greater than 0. And this time I'm not including 0 because yes, I can have 0 under the radical, but since the radical is in the denominator, I do not want a 0 on bottom, so therefore the square root of 2x minus 3, which is my denominator of this function, has to be greater than 0. Okay, so what I'm going to do is I'm going to go ahead and solve for x. I'm going to figure out what my domain is because the domain is the set of x values that work for this function. So what I'm going to do, I'm going to get rid of this square root right away. I'm going to square both sides. And when I square both sides, that leaves me with a 2x minus 3 is greater than 0. And I'm going to add 3 to both sides, which leaves me with 2x is greater than 3. So I added 3 right here to both sides. And to solve for x, I'm going to divide both sides by 2 because I'm multiplying by 2 here. The 2's cancel and I'm left with x is greater than 3/2. Now, another way to write that, 3/2 is the same as 1.5. So I know x has to be greater than 1.5 or greater than 3/2. Now, to write my domain in set builder notation, I'm going to say the set of x such that x is greater than 3/2 and x is an element of the real number system. If you remember using a number line, we're going to shade everything from 3/2. So here's 0, here's 1, here's 2. Here's 3/2 right here, which is at 1.5, and I'm going to shade everything greater than that. Okay. So therefore, my interval notation for this domain, I'm going to circle set builder right here. The interval notation for this function is parenthesis 3/2 or 1.5, comma, infinity, parenthesis. So if you wanted to use set builder notation, here's set builder right here. And interval notation is right there. So both are ways that you need to be comfortable with writing the domain. So I'm going to go ahead and list both set builder and interval notation when I respond to the question. In example 5, check for understanding. I would like you to state the domain of g of x equal to square root of x squared minus 16. You have 4 choices, A, B, C, and D. All 4 choices give you a set builder notation and a interval notation. Just so you know, this right here kind of got offset. This is part of the answer for part B. So bracket -4, comma 4 goes with this set builder notation, which is x such that -4 is less than or equal to x, which is less than or equal to 4. And x would be an element of the real number system. So down here, part D, they do not give you a set builder notation, but for A, B, and C, they do give you a set builder and an interval notation for the domain. I would like you to choose which answer best suits the domain of this function, and press submit when you're done.